All right, hello everybody. I need to apologize for two things. The first thing being that yesterday I recorded everything sideways, and my bad. That's not good. The second thing being is I recorded a lecture for you guys, and the video just disappeared. And so, in order to get class up in time, I'm going to be doing a quick run through of a lecture. I really recommend possibly just pausing on videos and reading things. I'll say stuff as well. I can't turn it around, Hillary. Oh. Sorry, my sister's here. And so I'm going to flip through all the stuff that I already recorded, and I'll just slowly walk through all the things that I did recently, and just so that I can get this lecture up in time. So first off, announcements. Quiz on Monday. It'll be available at the beginning of your normal class time. So if you're a 1:30 class, it's at 1:30. If it's a 2:30 class, it's at 2:30. And then you'll have an extra 15 minutes to turn it back in. And so you'll have until, if you start at 1:30, it'll be due at 2:35. If you start at 2:30, it'll be due at 3:35. You should be able to get them done in under 50 minutes. You have one old exam too due Saturday. Those are up on Canvas now. Just as a study thing, a recommendation would be to use one of the two more recent of the exams, because there are things worked out through it on the MLSE website. And then reminder, today I have a Zoom half hour, 3:30 to 4 o'clock Central available. So if you just want to contact me on Zoom, just look on the announcements for today's code around 3:30. All right. So just to emphasize, these are our three things that we care about right now. Antiderivatives, finding areas/volumes by cutting things up into slices or rectangles. And then going from a rate of change to a total change. And so okay. Here's the Riemann sum definition of the integral. So if we have, like over here, you have a curve f of x, and you want to find the sum or the area under the curve from A to B. The way you would do that is, number one, you'd set up that right here. This is the definite integral. So this means the area under the curve of f of x from A to B. But the sum definition is, you are going to add up the area of each rectangle, so delta xj, so this is your xj, times your height, so this is your width of your rectangle, and your height comes from your function f, plugging in that xj, taking the sum of all the rectangles from 1 to n, and then letting the number of rectangles go to infinity. So we're just adding up an infinite number of rectangles with area to find that area under the curve. All right, so as a focus, we have the general Riemann sum. And so if you have a curve f of x and you want to approximate the area under the curve, you might break up from A to B into a partition. So like I chose x, or A is x naught, and then you have x1, x2, x3, x4, and then this is x5, but it's at your B. Notice these are not an equal distance apart. Up until now, all our Riemann sums, which are the left, right, and middle, were an equal distance apart, but they don't have to be. They don't have to be. Also, you can determine your height of your rectangles at any point between, like for this one, between x1 and x2, including x1 and x2. So this first rectangle, we're choosing our height at C1, which is just somewhere in the middle. For our second rectangle, we're choosing our height on the right side. For the third rectangle, we're picking in the middle. Fourth rectangle, we're picking on the left side, and the fifth rectangle, we're picking somewhere in the middle. So it doesn't really matter where you pick for a general Riemann sum. And so when you're breaking this down, you'll see R of f comma p comma c. So R stands for Riemann sum. F is your curve. P is the partition, so that's your x naught, x1, x2, all the way up to xn, going from left to right, where x naught is A and xn is B, and C are the points you plug in for height. So that's your C1, C2, C3, all the way up to Cn. So it's your Riemann sum of your n rectangles, where you have your width, delta xj, which again is just your xj minus 1. So just like if you're looking at the width of your second rectangle, it's going to be x2 minus x1 to get delta x2. So you get the width times your height, which is your f of Cj, where Cj is just the point within your rectangle. You're plugging it in to get the height. So that is just a general Riemann sum. Okay. All right, so let's put this into perspective and do something with context. So a rocket is going the following speeds over the following times. So that top row is a time period in seconds. So from 0 to 1 seconds, the rocket is going 5 meters per second. From 1 to 3 seconds, the rocket is going 10 meters per second. From 3 to 4 seconds, the rocket is going 12 meters per second. From 4 to 9 seconds, the rocket is going 21 meters per second. And from 9 to 12 seconds, the rocket is going 30 meters per second. So pause, think. In reality, is this how a rocket behaves? No. It would have more of a continuous change going on in the speed. But this is a way that you could approximate it. So from 1 to 2 seconds, or 0 to 1 second, they measured that speed at the 1 second. So that's what that bottom right corner does. In the next time period, they measured the speed at the second. On 12, they measured it at 3. And here they're measuring the speed at second 6. And so it's just a way of approximating that speed. And so how far did the rocket travel in its first 12 seconds? So remember, speed is equal to distance over time. So distance is equal to speed times time. And so in that first second, from 0 to 1, it's 5 meters per second times 1 second. In that second time period, you have 10 meters per second times 3 minus 1 seconds, which is 2 seconds, plus 12 meters per second times 4 minus 3 seconds, plus 21 meters per second times 9 minus 4 seconds, and etc. And so you get that it's 232 meters. So if we look at our original triangle here, where we're looking at antiderivatives area, so what we did, we can look at it in terms of area. So this is a graph of this data up here. So from 0 to 1 second, it's going 5 meters per second, and etc. And so you take this height, this velocity times, or this velocity times this time. So 0 to 1 times 5. 1 to 3 times 10 to get that total distance traveled. But also, we're going from a velocity, so a rate of change of distance, to get a total change in distance. So we're looking at both of these in this problem. It just depends on your point of view. If you're looking at it graphically, it's an area, and you're breaking it up in a Riemann sum. And if you're thinking of it as a rate of change to a total change, so you can bounce between these two. They're the same thing, it's just a different perspective. Which, again, all three of these are the same thing, they're just a different perspective. So let's move on, and let's do something a little bit different. Okay, so a rocket's upward velocity is given by v of t is equal to 3.3 t meters per second at t seconds. How far did the rocket travel in the first 12 seconds? So real quick, I got this particular function by getting a best fit line of the previous page data. So this is supposed to match the data on the previous page. So we have a velocity, 3.3 t meters per second, and we want to find a total distance traveled. And so we are given a velocity to find distance. So velocity is v of t, distance is s of t because physics is weird. And so remember, velocity is the derivative of position. So v of t is s prime of t. So if we want to find the change in s of t, we need to find s of t. So if our s prime of t, v of t is 3.3 t, then what we want to do is we want to find s of t. And so looking at this, I'm just going to focus here. We know that it's going to be t squared because the derivative of t squared is 2t. But in order to get that 3.3 out front, we're going to want to half that 3.3. So 3.3 divided by 2. So when you take the derivative of 3.3 divided by 2, t squared, you're going to pull down that 2 to the front and you get 3.3. And then t squared becomes t. And so that's a proper s of t. But then we have one little extra piece here. We have plus a constant. Because the derivative of a constant is 0. So at time, so for our specific problem, let's just assume that the height of the rocket is 0. And so our distance is going to be 3.32 times t squared plus 0. So it's just going to be this guy for our specific example. But maybe we say that the rocket's on a platform at time 0 that's 10 meters off the ground. So then it might be 3.32 t squared plus 10 as your s of t. But we're just assuming it's 0. And so to find the change in distance, you just find the distance at time 12 and the distance at time 0. So that 3.3 over 2 12 squared minus 3.3 over 2 0 squared. And then you solve it to get that total distance change, which is 237.6 meters, which if you remember on the previous page, we had it was 232 meters with our approximations with that table. So these are related, which is kind of cool. And this, if you notice, we had a derivative and we found an antiderivative. So now we're using that top circle of our triangle on what we're focusing on. All right, so let's look at this graph of v of t. So it's a line, so 3.3t, and let's focus in particular from second 5 to second 6. If you wanted to approximate the distance traveled from second 5 to second 6, you might choose a velocity in there and just to fix it. And so I'm going to pick the middle velocity at 5.5 and plug that in. So it's going to be 3.3 times 5.5 and then multiply it by the change in time. So that's 6 minus 5. And we get from second 5 to second 6, it travels 18.15 meters. So we're looking at the area under the curve of velocity. And so when we're looking at those bottom two pieces of our triangle, to find a total change, it's the same thing as finding the area under the rate of change curve. So under the derivative curve gives you the total change. So the area equals the total change under the rate of change curve. And so I wrote that down. Area under the rate of change curve, which is the derivative, is the total change of the antiderivative. And so those two pieces are connected in that way. So that makes some really, really cool things happen. It means that we can use strategies where we find antiderivatives to find areas under the curve. So let's do something a little bit more abstract. Okay, so find the area under the curve of y equals x squared from x equals 4 to x equals 7. And so here's a very rough graph of x squared from 4 to 7, and I drew in those little rectangles so that you can see. Yeah. And so if we were to set this up, I'm going to focus on real quick. You want to start by finding that delta x. So we've got our total change in distance, which is 3, divided by our number of rectangles, which is n. So whenever we put it into our Riemann sum for our width of our rectangle, we're going to have 3 over n. Now let's look at our height of our rectangle. So our first rectangle, if we're looking at a right sum, so determining the height from the right side of each rectangle, that first rectangle get its height at 4 plus 1 of your widths, so at 4 plus 3 over n. So you plug in 4 plus 3 over n into your function. So it's going to be 4 plus 3 over n squared. Second one, you're going to be 2 widths over that you plug in, so it's going to be 4 plus 3 over n times 2. And then to get the height, plug this value into your function, so you square it. And then for the third rectangle, you're going to be 3 widths over from 4, and so you have 4 plus 3 over n times 3, and then you plug that into your function in order to get your height squared. And so on the jth rectangle, you're going to have 4 plus 3 over n times j, and you're plugging that into x squared in order to get your height. And so the area of the jth rectangle is 3 over n, your width, times 4 plus 3 over n times j, all squared to get your height. So width times height to get the area. You're summing up from j equals 1 to n of your rectangles to get your total sum. And then we're letting the limit of the number of rectangles go towards infinity. And so I'm going to do some scratch work. And I'm going to square 4 plus 3 over j over n squared. And you get 16 plus 24 over nj plus 9 over n squared j squared when you FOIL that out. And then I'm going to distribute that 3 over n through there. And you get 48 over n plus 72 over n squared j plus 27 over n cubed j squared. Okay, so just we are distributing that 3 over n into here to get this. So then we return to our Riemann sum definition of an integral, and we're going to plug in these new values. Okay, so when you plug these in, the limit as n goes to infinity of the sum from j equals 1 to n of 48 over n plus 72 over n squared j plus 27 over n cubed j squared. And then we can pull out constants and separate the sums by term. So we're still going to let the limit of the number of rectangles go to infinity. And then for this first term, we can pull out 48 over n because in our sum, n is not changing. J is changing. And so we pull out 488 over n and we're left with 1. Plus, for this next term, we can pull out the 72 over n squared, but leave the j within the sum. And for the last term, we can pull out the 27 over n cubed and leave the j squared. And so we go back to when we learned power sums. And so remember, the sum from j equals 1 to n of 1 is going to be n. The sum from j equals 1 to n of j is going to be n squared plus n over 2. And then the sum from j equals 1 to n of j squared is going to be 2n cubed plus 3n squared plus n over 6. And so we've replaced the sums with our power sums, and then we're going to distribute these out. And so you have 48n over n, and then when you multiply these, you have 72n squared over 2n squared, plus 72n over 2n squared. Then over here, 27 times 2n cubed, so you get 54n cubed over 6n cubed, plus 27 times 3n squared gets 81n squared over 6n cubed, and then 27n over, oh, that should be 6n cubed. There's a mistake. All right. And then we notice all the ones that have the same power of n in the numerator and denominator. So n over n is always equal to 1. N squared over n squared is always equal to 1. And n cubed over n cubed is always equal to 1, except where n is 0. And so if we look at those three pieces, as n goes to infinity, like it's just the n parts are going to 1. So we're just left with 48. 72 over 2, and 54 over 6. And so those pieces are just going to be those numbers. But then if we look at the other three terms, we have 72n over 2n squared. Well, n squared is growing a lot faster than n. And so you're going to have ultimately a smaller number over a much, much, much bigger number. And so these pieces, this is shrinking and going towards 0. This piece, n cubed, grows so much faster than n squared. And so this term eventually is going towards 0. And on this one, n cubed is growing much, much faster than n. And so this piece is going towards 0. So when you take the limit of everything, you are left with 93. Okay, so that was a lot of work. What if we change our perspective? All right, suppose that y is changing at a rate of y prime equal to x squared. So y units over x units. So the way to think about this is you've got at x equals 1, y is changing at 1 squared, which is 1, y units per x unit. So the slope at x equals 1 will be 1. But let's say at 4, y prime is going to be 4 squared, which is 16, so 16 y units per x units. So the slope at 4 of y is going to be 16 delta y over delta x, okay? So what is the total change in y from x equals 4 to x equals 7? All right, so y prime is equal to x squared. So then if we were to backtrack and find our antiderivative, then we would go up in our power, but then in order to have 1 in front of our x squared, you need a 1/3 out front, because the derivative of 1/3 x cubed, you pull down that 3, it becomes a 1, and this becomes x squared. That's good. But then we need to add a constant. We don't know what constant, because the derivative of any constant is 0. and we aren't given any information about the starting value of y. But it turns out it doesn't matter because we're looking for the difference from 4 to 7 of y. And so we plug in y of 7 minus y of 4. So that's 1/3 7 cubed plus c minus 1/3 4 cubed plus c. Don't forget the parentheses. And then plus c minus c. So these cancel out. And so you end up with 1/3 7 cubed minus 1/3 4 cubed. And that gives you 93. And so what took us a whole page and like 20 minutes on the previous page, I'm exaggerating, only takes 2 minutes using this strategy where you think of your curve as being your derivative and you're trying to find the total change or your area under the curve of your original or antiderivative. And so you find your antiderivative and you find that difference. And this idea of connecting these two, of the area under the curve, by using an antiderivative to find a total change, is called the Fundamental Theorem of Calculus Part 1. So the Part 1 just comes from your book. There are 2 parts of the Fundamental Theorem of Calculus. The one we're looking at today is for a definite integral. So you have a starting point and an ending point. In the future, we're going to look at antiderivatives and integrals that don't necessarily have starting points or ending points. And so we're going to learn a little bit more about those. But today we just care about this. And so for your you-do, I want you to find the area under the curve, y equals x cubed, from x equals 1 to x equals 2, using 1, the Riemann Sum definition of the integral, and 2, the fundamental theorem of calculus. So for the fundamental theorem of calculus, assume your derivative is 8x cubed and find your total change in your original or your antiderivative y from x equals 1 to x equals 2. So I want you to do both ways and just get a feel for that. And then just to remind you, I do have a Zoom 30 minutes from 3:30 to 4 today. And a really, really good way to use like our time wisely is do your you-do question. And then if you have questions about how to do that, check in with me on that day for Zoom. Like, I think that'd be really, really valuable. I know it's easy to kind of just watch these videos and pretend like you're learning, but these you-dos actually make sure you know what you're doing when you're learning. So please, please, please be doing these you-dos. And speaking of last time's you-do, you had to find L5 and Ln of y equals 2 over x from x equals 1 to x equals 4, so the left sums, and then also set up the Riemann sum definition of the integral on that interval. And so for L5, you're going from 1 to 4, so your delta x is going to be 4 minus 1 over 5, which is 3/5. And then the area of each rectangle is going to be 3/5 times the height, and your height comes from that 2 over x. And so for the left one, your first rectangle gets your height at 1, and so it's 3/5 times 2 over 1. Your second rectangle is going to be 3/5 over from 1, and so it's going to be 2 over 1 plus 3/5. Your third rectangle is going to be 2 over from 1, so it's going to be 2 over 1 plus 3/5 times 2, and et cetera, and et cetera. Notice that we end at 4 for 5 rectangles. And so we get that approximately, with L5, we get 3.277. All right, so then if we were to set it up with n rectangles instead of 5 rectangles, the only thing that changes is that your width is now 3 over n. But similarly to like the 5 one, your height is just going to be 2 over 1 plus 3 over n instead of 3 over 5 times j for the jth rectangle. And for a left sum, remember you want to start counting at 0 and end at n minus 1. So up here, we started at 0, and we ended at 4, which is 1 less than 5. And so j equals 0 to n minus 1 of your width, 3 over n, times your height, which is 2 over 1 plus 3 over nj. And then remember, you can also pull out that width in front of your summation, so you can factor it out. Either of these is acceptable to write Ln. And then for your Riemann sum, like the only thing you have to change is let the number of rectangles go to infinity. So you can keep your Ln. We haven't really done a Riemann sum with the left sum, but remember, like it doesn't matter as long as you let your number of rectangles go towards infinity, is equal to this definite integral from 1 to 4 of 2 over x dx. So yeah, that's your problem. And then just to remind you, I made a mistake at the end of class on, let's see here, yesterday. And I figured it out. I just can't add and divide. So I said 48 over 6 was 7. It turns out 48 over 6 is 8. And 6 plus 12 plus 8 is 26, which is what we thought, or what I thought it should be, using that fundamental theorem of calculus. And so that was my bad. But anyway, that's the end of class today. Again, I'm sorry this is so fast. Again, I recorded like a 50-minute version of this lecture as I wrote, and it just deleted instead of uploading. So my bad. Yeah. So feel free to press pause on this video or rewatch pieces and ask me questions, because this stuff is really, really important. So have a wonderful rest of your day.